Well, we've looked at the difference between physical and chemical properties. Today we're going to look at the difference between chemical properties and chemical reactions. And we're going to start taking a look at different ways that we can use patterns that we see in chemistry to predict the products of chemical reactions. A chemical property is really only just a description of a possible chemical reaction, a potential chemical reaction that might happen. A chemical reaction is actually taking place when either two or more substances combine and change, or it's also a chemical reaction when a compound decomposes. So you could have a single substance, as long as it's a compound, and it decomposes. There are 5 reaction patterns that we're going to look at in this class. One is called synthesis reactions. Synthesis reactions have this general characteristic. You start out with 2 or sometimes more reactants, and you end up with a single product. And this is the kind of generic equation for a synthesis reaction. Start out with 2 things, and you synthesize or create one product. A decomposition reaction looks almost the opposite. You start out with a compound, and you decompose it into 2 or sometimes more products. Single replacement reactions, you start out with one element, and you start out with a compound, and you sort of replace one of the elements with the other. And so you end up with a different element and a different compound. Double replacement reactions are like 2 single replacements happening at the same time. You start out with a compound and another compound, and then 2 of these partners switch. So you end up with a different compound and another different compound. In a combustion reaction, I'm always combining oxygen with something. So I may start out with an element, add oxygen to it in a chemical reaction, and end up with an oxide of that element, AO something. Or I could start out with a compound that has a couple of elements in it and combine oxygen to it. Could even have more than 2. And in that case, I'll end up with a couple of oxides. So I'd end up with AO something and BO something. Well, today we're going to focus on the first 2, which is synthesis and decomposition reactions, and then we'll take the other ones in their turn and look at them in more detail. In a synthesis reaction, remember the generic equation is A plus B makes AB. So you're synthesizing or creating a single product. It's easy to spot synthesis reactions because of that. They have a single product, but they have more than one reactant. Now, how do we predict the products? Well, if the reactants are a metal and a nonmetal, it's easy to do. An ionic compound is going to form. And when that takes place, we just use the charges on the monatomic ions to predict what the product is going to be. Let's take a look at an example. If I react sodium with chlorine, I'm reacting a metal, sodium is a metal, with chlorine, a nonmetal. That means my product is going to be ionic. What is the product? Well, I can use charge swap to figure that out. Sodium is 1 plus because it's in column 1. Chlorine is a halogen, a column 7, that's 1 minus. When I charge swap, I just get NaCl. So the reaction is Na plus Cl2 makes NaCl. Now this isn't balanced, obviously. I've got 2 chlorines here, but only 1 on this side. So I'd have to balance that with a 2, which would then give me 2 sodiums, so I'd have to balance that with the 2 in front of the Na. And that gives me a balanced chemical equation. Well, here's the reaction happening. We've got a piece of sodium. This guy's putting this inside the flask. Inside the flask is some chlorine gas. You can't really see it. It's sort of a pale yellow color. There's also some sand to absorb heat so the glass doesn't crack. And he pokes a piece of sodium in there. Nothing's happening at first. So he's going to add some water. Just a drop of water is going to go down through that tube that the sodium went in. And when the water hits the sodium, it starts the reaction happening. So it's a violent reaction, you can see. And in the end, there's a whole bunch of kind of smoke-like stuff in there. But also laying in the bottom of this flask is going to be sodium chloride. Here's another synthesis reaction. And again, it's between a metal, aluminum, and a nonmetal, oxygen. So we're going to predict the product by just doing a charge swap. Aluminum, column 3, 3 plus. Oxygen, column 6, 2 minus. When I charge swap, I get Al2O3 as a product. So Al plus O2 makes Al2O3. This isn't balanced. I have 3 O's and 2 O's, so I'll put a 3 there to make 6, a 2 there to make 6. That gives me 4 aluminums, so I balance that with a 4. Another example, again a metal, iron, and a nonmetal, oxygen. Predicting this product is going to be a little more challenging, and that's because iron is a transition metal. Because iron is a transition metal, I have two options. It could either be a 3+, which would give me Fe2O3, or it could be a 2+, which would just give me FeO. I'm going to try not to ask you to do any of these on tests or quizzes, but if I do, either answer will have to be equally valid unless I give you some clues. Now, if the reactants are both nonmetals, or nonmetal and a metalloid, or both metalloids, then a molecular compound or a covalent compound will form. And that's going to be quite a bit more difficult to predict the product for. Our knowledge of Lewis structures can give us some clues, though, that might help us to at least eliminate some answers that can't be right, or give us some good hints about the likely products. Like take this, for example. Hydrogen is reacting with oxygen. I know when I'm drawing skeletons for Lewis structures that oxygen prefers to make 2 bonds. I also know that hydrogen has to be on the outside of molecules, and so that sort of leads me to the conclusion that H2O would be a pretty good product here. It's not balanced. A 2 here and a 2 here will bring it into balance. Now in that last example, you don't have to get water. There are other possibilities when hydrogen and oxygen combine, but that's the one that's most likely. It's your best first guess. Here's another example. If I have carbon, I know that carbon prefers to make 4 bonds, because it's column 4. Chlorine is a halogen, and those are often on the outside. So what makes sense is a skeleton starts out like this. 4 chlorines on the outside of a molecule that has carbon in the center. So CCl4, that's a reasonable structure. In this example, there's another thing that I can get from what I know about how chemicals behave. I know that this one, CCl5, that's not possible because carbon is a period 2 element. Period 2 elements can't have expanded octets. So CCl5 or CCl6, those can't possibly be the right answer. So sometimes I can eliminate some wrong answers. Sometimes I can get a decent clue about what a likely answer would be. Decomposition reactions, which are sometimes called analysis reactions, are almost the exact opposite of synthesis reactions. The generic equation looks exactly the opposite. I start out with one thing, AB, a compound, and I divide it up into more than one product. So these are easy to spot because they only have one reactant, but they're going to have multiple products. How do you predict the products? It's pretty easy. If you have a binary compound, which is what you're usually going to have, you just list the elements. Now, as you're doing that, don't forget the diatomics. Here's an example, Al2O3. This compound is made of 2 elements. One is aluminum, that's not diatomic, and the other one's oxygen. Oxygen is diatomic. There are your products. Now, if I wanted to balance this, I'd have to put a 2 here to balance 6 O's with a 3 here. That would give me 4 aluminums, so I'd put a 4 there. Another example, calcium and chlorine. Calcium is one element, not diatomic. Chlorine is a second element, is diatomic. It's already balanced. Another one, Na2O, decomposing. Well, sodium, not diatomic. The second element here is oxygen, which is diatomic. To balance this, I could put a 2 here to balance my oxygen. That would require 4 sodiums on the right, so I'll put a 4 there to balance. Here's an example of a decomposition of a familiar compound, water. We've done this in class before. These people have a slightly fancier apparatus than we did. And you can see that the hydrogen and oxygen separate out. So the decomposition is H2O decomposes to make H2 and O2. And the formula is shown by the spaces, the size of the spaces. 2 H2s are produced for every 1 O2. And that has to be balanced with the 2 in front of water.